Non c'è audio in sala, eh? Il microfono dello speaker non sta andando.
Switch it on. Okay. Mm. Better to use this one.
Sometimes work, sometimes not.
Okay.
Hoe staat het hier poco tempo fa? Questo forse?
Is this saying low battery or no?
No.
On, just on.
No,
No,
but-
battery is full.
Prova a fare switch off.
Cosa fa il volume?
Prova a spegnere o riaccenderlo. Non si fa. Sì, mute. Mute.
Ah, now it works.
Is that working? Yes.
Elisabetta, puoi chiedere al system manager di venire? Dov'è questo? Ma non è ancora in linea?
Remove the banner.
If you know how to do it.
Okay. Okay.
Yeah.
Yeah, please remove audio from the laptop.
And then check your output is off.
My what?
Yeah, please remove the audio, the speaker
Yeah.
and the microphone from the laptop.
I don't
Check
know.
it, please.
The volume of your laptop.
And it's here.
Okay.
Okay. That's a, thank you. I think.
We go. All right. Good morning, everyone. Thanks for coming. So it's a pleasure for me and an honor to introduce today's speaker, Professor Andy Fabian. So let's call him Andy because we know since many years. For those of you that do not know Andy, I think I would say he's a piece of X-ray astronomy because he started, can I say, 50 years ago. You are not offended if.
No.
And I mean, he made a very important, relevant, seminal contribution to the study of AGN, cluster of galaxies, X-ray background, and many other topics. Not only, mainly based on the X-ray astronomy, but not only. And he was involved in essentially all X-ray missions since the time of Ariel 5, maybe, or Exosat and on. And he's also involved in the future X-ray mission. And he was awarded of several important prizes, the Royal Astronomical Society Medal, the Bruno Rossi Prize, and the Kavli Prize in Astrophysics. Today we'll talk about the X-ray universe, 50 years of X-ray astronomy. So, Andy, thank you very much. I don't know if you need this. Yeah.
Well, thank you very much for coming to hear this. I'm going to talk about some threads in my work in X-ray astronomy over the last, it's now 55 years, a long time. And let's go to the first slide. This is from when I was a PhD student. Here is me, here is a helicopter. And this is the Australian desert in January 1971 with a temperature of 30 plus because it's the Australian desert. And I started out my PhD in 1969 and started out in rocket X-ray astronomy. And this was my first rocket flight. And you can see the parachute didn't work. So when you drop down from 100 kilometers, without a parachute, that's what happens. And that is the X-ray detector that I worked on. And there are some electronics associated with it that I designed and had built. And that is the launch. So I was trying to look at what's called the X-ray background, which had been discovered in 1962 in the first flight, the first X-ray astronomy flight by Riccardo Giacconi and his colleagues, which went from the US, and they discovered in that first flight one source, which was SCO-X1, which is the brightest X-ray source in the sky. And they also observed that there were X-rays all over the sky, fairly uniformly, but not precise. And I was going to try and measure how non-uniform it was. And this is now jumping ahead 30 years from that. This is what XMM finds the X-ray sky to look like. This is a region almost the size of the angular size of the full moon. And you see that the X-ray background is made out of lots of little dots. Most of these are accreting supermassive black holes. And these fluffy things are the clusters of galaxies. Puddles of gas trapped in the potential well of clusters and groups of galaxies. And I just mentioned there that back in 1992, Xavier Barcons and I wrote an annual reviews article on the X-ray background. Many of you will know Xavier Barcons. He's now the Director General of ESO, which I didn't expect to happen back then. Anyway, let's talk about clusters to start with. Clusters can morphologically be divided into two types, cool core ones and non-cool core. And they're roughly 50-50. Depends upon how you make your definitions as to what the split is. But this is our surface brightness representation of X-ray surface brightness. And this is plus or minus 1 megaparsec either side of the center of the cluster. And the cool core ones, like Abel 478, have got very steep spike in the middle. And the ones like the Coma cluster, which are non-cool core, just have a sort of little bump there. They are both very highly luminous clusters, 10 to the 45 ergs per second in X-rays. And the X-rays are made by Bremsstrahlung of the hot gas. The gas in this one is probably, well, it is, we know it's 10 keV, which is around 10 to the 8 Kelvin. And here, this enormous spike in the center, which had been discovered early in the 1970s, is due to the fact that the gas in the center of this cluster is the radiative cooling time due to emission of the X-rays we see, and they're generated by Bremsstrahlung, a two-body process, electrons interacting with protons principally, leads to the cooling time getting shorter and shorter towards the center of the cluster. And the gas should flow inwards because it's losing its energy and it should slump inwards subsonically at rates of hundreds of solar masses per year in a rich cluster like Abell 478. And the reason there's this spike is because the temperature is cooler for the gas near the center, and therefore the density has to rise to make the pressure that supports the weight of the overlying gas. And that then forces this cooling flow. And at rates of hundreds of solar masses per year, this is a very large rate. What happens to that gas? And it led to the concept of cooling flows, which and independently two groups, Len Cowie and James Binney, and myself and Paul Nelson, a student of mine, we had papers on cooling flows in 1977. And this is the same year that Rees and Ostreicher and Joe Silk and many others came out with the first papers on the formation, how do galaxies form in the universe? And basically, it's dark matter potential wells are developed early in the universe, and the dark matter wells then allow once the gas has been, we've gone through the dark ages, once we're free to move, it then falls into these potential wells, shocks and heats up to the temperature of the potential, which is around 10 to the 8 K for a rich cluster and a few 10 to the 7 K for a poorer cluster. And so that's what is a cooling flow, just in a very short way. I wrote a review of it in 94, and to show the brightest cluster in the sky, the Perseus cluster, let's go and look at a nice optical image. This is made by an amateur astronomer with a 20-inch telescope of the Perseus cluster. And you can see this spectacular object here. That's NGC 1275. It looks like a squash spider or something. But these are all elliptical galaxies in that cluster. And now let's look at it in X-rays and superposed. And what we see is all the diffuse emission that's between the galaxies. In a cluster of galaxies, I'll remind you that there's more gas, or baryons, if you like, than there is in all the stars in the cluster. Roughly, there's 3 times more gas in the intracluster medium than there is in the stars in the galaxy. And together, all the gas accounts for about 17%, to be more precise, of the total mass of the cluster. The bulk of the mass of the cluster is in dark matter. And we still don't know what dark matter is, and maybe it'll be announced tomorrow, maybe it'll be announced 100 years from now. I think we have little idea what dark matter is. There's lots of people will tell you they think they know, but it's still a very open problem. Another issue here is the galaxies, the elliptical galaxies, go back here. You'll notice that these bright elliptical galaxies also appear in the X-ray image, and that's because, let's go forward, the X-ray emission is coming from the black hole at the center. And this innermost region here is where the central black hole of NGC 1275 is. And you'll see that there are these holes either side. Some people call them cavities. I'm going to call them bubbles, have been blown by a radio source which has jets going north and south, which is filling these cavities up with sort of cosmic ray plasma. And this is the radio emission sitting in this surroundings, and it's surrounded by a harder X-ray emission, which is confronted by a shock. So the bubbles are being blown by the jets and expanding outwards. And then there are outer bubbles, which are here and here. So the bubbles eventually are buoyant in this plasma, and they rise up and form this bubbling process. And what happened in the early noughties, the 2000s, much of the cooling was realized, the radiative cooling was balanced by heating, probably from these bubbles. And this is a typical plot from the time where you plot cooling luminosity versus cavity power, we can work out what is the power of those cavities by the energy in the cavities is P times V, and P is the pressure you can measure from X-ray observations of what the pressure is in the center of the cluster. V you can get from geometry, so you've got the energy of the cavities, and then you multiply that by or divide it by a time scale on which you think the bubbles are forming, and there's some, I won't go into the details of the time scale, but essentially the cavity power is worked out, and this is cooling luminosity, and there's a sort of correlation, which for an astronomer, it's a good correlation. For, purists, it's not a very good correlation at all, because each of these is, a factor of 4 separating them. But you can see other objects which have got the bubbles, and they're very common in the cool core clusters. Also, when you look at the image, you can massage these images, the X-ray images. What was found was the image looked quite sort of ripply. And back in 2003, with the Perseus images that we made, we thought that this was sort of showing us what was going on. In other words, there were sound waves being propagated out from the bubbling process at the center. And the bubbling process may be a bit like a fish tank aerator, where there's a continual flow of energy at the bottom, making bubbles which are then rising and pinching off, and then a new bubble forms and so forth. And the bubbling process is sending out successive sound waves which propagate through the cluster. And that's how energy gets from the black hole out to the surrounding cluster. I would say that that was not a very popular interpretation, but I've played with it for a long time. Many people believe that what's going on is there's turbulence in the cluster. The bubbling process creates a lot of turbulence. It's that turbulence which drives the heating of the gas. And if it was Kolmogorov turbulence, you churn things around on big scales, and those big scales make eddies on smaller scales and on yet smaller scales, and the energy flows from large scales to small scales, and then is dissipated by some sort of process, friction or something like that on small scales, heating the gas, and maybe that's what's going on. So one big question in this area is, how is energy transported across the cluster? Is it due to turbulent motions or sound waves? And we're now able to sort of tackle part of that problem. And to start with, this was the result from the Hitomi satellite, which was short-lived and lived in 2016. And it took measurements of the spectrum of the center of the Perseus cluster. This is an outline of the detector aperture. This is the spectrum it made in X-ray spectrum. And it was an amazing thing to get an X-ray spectrum with such high resolution. We could see all the individual lines. This is because it was a microcalorimeter. Most of our spectra are made with CCDs, which have a spectral resolution of about 150 to 200 EV at 7 kV, whereas this had a resolution of 4.5 EV. And that's because it was operated at 50 millikelvins. And when an X-ray comes in, then an X-ray comes in onto a detector, onto an absorber. The temperature rises by a few millikelvins, and you can measure that temperature rise with a thermistor, an electrical device, and then the energy decays away down this thermal link into a heat sink. So, but this is operated at 50 millikelvins. Operating a spacecraft detector at 50 millikelvins is difficult. You need to put it all in a dewar, et cetera, and it's complicated. But so we got this wonderful result from the Perseus cluster in 2016, and it showed that the velocity of the gas in the Perseus cluster was about 160 kilometers per second, which is low. I'll get round to that in a minute. There was a reflight of Hitomi, which was launched in 2023 called PRISM. That's how you spell it, okay? This CRISM satellite has got a couple of telescopes on, one of which also has a microcalorimeter. It's a complete copy of the one that was in Hitomi, and it's working superbly, apart from one thing, and that is the dewar in which the detector is. That's the sort of thermal vacuum flask it's all put in order to keep cold. It has a hole at the top, and there's a lid on it so that you can operate it on the ground. And that's called the gate valve. And that, after launch in 2023, they tried to open the gate valve a couple of months later, and it didn't open because something's jamming it shut. And they've tried heating, and by orienting the satellite in a certain way, and also shaking things on the satellite, something in the dewar pumping system they can shake around, and it hasn't opened so far. But they're going to try again this September, sort of 2 years after launch, and hopefully the gate valve will open. We keep our fingers crossed. It's thought that it's only of the order of a millimeter nudge that's required, but it's keeping it close. That means with the gate valve closed, and the gate valve isn't completely opaque, it's got a beryllium, it's a thick bit of beryllium, which is, it cuts out soft X-rays, and then it's got a metal grid on top of it to hold it in place. And this is what the effective area of the instrument is. And if it opens, it'll come up to an effective area like that. It's going to increase it a lot at all energies, but particularly below 2 keV, suddenly the soft X-rays are going to be available. So fingers crossed for September. I mean, the worst case is it does move and half opens and blocks the light, but let's be optimistic. Anyway, what does the coma cluster look like with CRISM? Here it is. The paper came out last week on Archive. Here is the coma cluster. It's a Chandra image underneath. There were 2 pointings here and here, and you can get the scale here. And these are 2 prominent giant galaxies in the coma cluster. And what's surprising is these spectra are very sharp. They indicate relatively low velocities, relatively low. And this is the velocities. And what we find is the velocities. So what you're looking at is the integration along the line of sight in those pixels. These are sort of meant to be separate independent pixels. And the mean velocity is minus 450. And the mean velocity of the southern observation is minus 730. So between there and there, there's quite a velocity difference. So over a few hundred kiloparsecs, we're getting a nearly 400 kilometers per second difference, or certainly 300 kilometers per second difference. But you notice within each one that they're very similar. So on small scales, there's not a lot of difference. And when you look at the velocity, so that's just the mean velocity of the line, provides that information. But when you look at the width of the line and correct it for instrumental effects and thermal broadening, you end up with these answers. It's 210 rather there, with those all rather similar. And this one down here is 200 plus or minus 30. So we have an effect where it looks like the amount of turbulent energy is relatively low. And if we look at the pressure in kinetic energy versus the total pressure in these objects, it's around, from these results, around 3%. So 3% of the total thermal energy of the gas plus all other energy is in kinetic energy, turbulent energy. And this is a cluster that's just had another subcluster go through the middle of it. So it's had a collision. It should be a big mess. Everybody expected it to be a really messy thing with velocities all over the place. And over here, you've got examples of, these are computations, numerical computations of clusters of galaxies. There's a big industry, maybe somebody here works in that industry of making computations. And these are all results of, in particular where they're solid, they are of coma-like clusters. And what you noticed, I hope, is that this CRISM result is only, and most of them, there's no mean actually of the same value, and they're only at the edge. So this is telling us that the observations are at variance with the theory. And I'm not going to go into this plot at all in detail. This is a velocity structure function, but let's just look at this one over here, where people who make these plots, they love to put them against inverse distance. So spatial frequency versus the velocity. And this is what comes out if you plot just the velocities. You end up getting a line something like this. And it's not that too bad with regard to Kolmogorov slope on this, which should be goes -11/3. But when you add the velocity dispersion in, which is around 200, then you get a result that goes down there. So in other words, the results are indicating that there's quite a lot of power on large scales, but when you go to smaller scales down here, across here on the right, then there's not much power. So this is telling us it doesn't look as though there is energy being transferred in a Kolmogorov fashion, in which, I mean, it's early days, but we're looking forward to, there are new and more observations of coma being done and of many more clusters. But this is, I was talking to Gianfranco Brunetti yesterday, and we were sort of talking about how there's going to be a revolution in understanding about intracluster gas. And this is one of the signs of that revolution. And this came out on Monday on arXiv, the Hydra A cluster from Brian McNamara and Tom Rose and colleagues. And this is what that cluster looks like. This is a cool gold cluster with bubbles. And you can see inner bubbles. And this is not a very good picture. This is a better picture showing the bubbles in the center of this cluster. And that's where the radio matches. And this is what the spectrum looks here. The velocity dispersion is 164. It's almost exactly the same as Perseus. Okay, this is a big, rich cluster out there with a low velocity dispersion. And one of the things that I will point out in terms of turbulence countering cooling, radiative cooling, then if the thermal energy is, say it's only 3% of the total energy in the cluster, that if the kinetic energy is only, say, 3% of the total energy in the cluster, then after 3% of the radiative cooling time, it will have radiated away the energy, its energy, that's kinetic energy. And so you need to find a way to resupply it. And if you're resupplying it over a radius R, you need a timescale of T cool, but it's got to be that fraction of T cool, that ratio. And so this means you end up requiring much higher velocities. And for Hydra A, you need a velocity of 540 kilometers per second. So something has to move at hundreds of kilometers per second, and we only measure 164. So there's a problem if you want to make turbulent energy resupply that gas. And this is the current status. There are more results which I don't have, but the Perseus is there. 2029 is 169. Centaurus is less than 120. Hydra A, 164. And the typical result for the ratio of kinetic to thermal is 2 to 3%. So they're all roughly the same. So I've just told you, I'm interested in sound propagation. And those ripples I showed you earlier from Chandra. So what about sound as a way of propagating energy in large clusters. Now, all of you know that in space, no one can hear you scream. But provided you scream with a frequency which is, say, the inverse of the collision time of the particles, you are making sound waves, okay? And that means in a cluster that particles don't collide much, but it does mean, provided you're talking about frequencies of once per million years, once per 10 million years, then you can have quite powerful sound waves. So what I'm arguing is the bubbling process, which is operating on a few 100 million year timescales, is sending out weak shocks, pressure waves out into the cluster, which are bona fide sound waves. Now, the nice thing about sound waves is they can propagate energy very efficiently with very small displacement velocities. Remind you about how sound waves work, okay? They're a sort of coherent thing where the particles all have a component of energy or motion all in the same direction, but it's not their full thermal motion that is in that direction. It's just a tiny bit of it. And when I'm talking here, then the displacement amplitudes of the air are nanometers. They're tiny, okay? If I make, and as I increase the loudness, of course, what's happening is the amplitude is bigger and bigger, and the displacement velocity gets bigger and bigger until the displacement velocity equals the speed of sound, in which case you get a shock. Okay, so that's how sound waves work. But this means the energy flux due to sound waves compared to if you did random motions, it's quite a lot larger in terms of ratio of the sound speed to that displacement velocity. And so you can, with like 100 kilometers per second, but if the sound speed is 1,000 kilometers per second, as it is in Perseus, it's perfectly okay. So I'm happy with these low velocities. Okay, now on to these cooling flows I started off talking about that we have been looking at. When XMM was launched, it still has a couple of reflection grating spectrometers on, which are not as high resolution as CRISM, but the soft X-rays they are pretty good. And you can then get high resolution spectra in the soft X-rays from them. And this is an example from an ESA announcement back in about 2005, where this is the spectrum of this cluster. It's a cool core cluster 2A0335. And you can see there are some emission lines, but the prediction for a cooling flow is these massive emission lines. And there was a lot of discussion 20 years ago about what's going on. And it implies simply that less than 10% of those cooling rates of hundreds of solar masses per year can be correct. And one possibility is the gas only drops to 1/3 of the outer temperature. But I didn't like that solution because you don't see it piling up at a particular temperature, you just don't see it. So, but anyway, essentially cooling flows became dead and nobody worked on them, including me. And let's go to the Centaurus cluster. That's what it looks like. And we worked on this, and Jeremy Sanders went and looked at the mass cooling rate as a function of temperature and found that the mass cooling rate dropped steeply with temperature as you went to lower temperatures, softer X-rays. Now, if I told somebody who works on active galactic nuclei, it looks like we don't see much emission in the soft X-rays from your active nucleus, all they'd say is there's absorption. And it's quite common for supermassive black holes to be surrounded by absorbing gas. So could that be the answer? Is it possible that absorption of the soft X-rays is causing this effect? And we thought we'd discovered this back in 91, and we had papers like this and this, but it wasn't very popular. And I wrote a review with John Peterson in 2006. I said absorption has generally been abandoned as an explanation, although no detailed test has been made of a model in which the absorption is intimately linked with the coolest cooling gas clouds. So you can't just sort of bung any old absorbing material into a cluster and make the spectrum work. You have to make it be right next to where you want the absorption to happen, where the emission is taking place. So if you do it in the same place, and imagine the gas is cooling, it produces cold gas, and cold gas can then absorb other X-rays, and imagine you've got mild turbulence mixing it all around. That's what I have in mind. Then you can get this. And there's a sort of multi-layer intrinsic absorption model that Steve Allen and I came out with when we worked on ROSAT data, and that works and works very well. The energy from the gas cooling below 1 keV has to come out somehow, and let's say it's emitted by dust and gas in the far infrared, and ultraviolet and optical and infrared. This is what the Centaurus RGS spectrum looks like. And when I fit this model, the hidden absorbed cooling flow model, I thought of calling it the absorbed cooling flow model, but then that's my initials, so it's a bit presumptuous. So I've called it hidden cooling flow. Here, that's what the spectrum is like, and it fits very well. And from it, I conclude that the mass cooling rate is around 16 solar masses per year, and the column density is around 1.5 times, that's the total column density, although the gas is distributed, is 1.5 times 10 to the 22. And it gives a very good fit. If the gas cooling, absorbing gas was not present, the spectrum would look like that. That's what if I just remove the absorption, what it would look like. And it doesn't look like that, but that's showing you how much it's been depressed by the absorption. The center of the Centaurus cluster, I managed to get it with HST about 10 years ago, and it's spectacular with this, the nucleus is here, and you can't see it clearly, but it has a sort of S shape on it. But you can see it surrounded by a lot of absorbing material. And if you look up there, which is just, it's the same thing, only with a different sort of adjustments, you can see their absorbing gas is extended all over this. And when you look with Herschel, this far infrared satellite ESA had back in, we used it around 2010, 2012, looked at the Centaurus cluster, there's an enormous bump in the infrared, and that is the emission. That emission is equivalent to 12 solar masses per year cooling, which is balancing what we inferred to be cooling. So the whole thing works, I believe. And the hidden cooling flows are common. These are HSTs at the center of NGC 5044 group, and you can see there's stuff all over the place. This is the center of the Abell 262 group with a big dust, I won't call it a lane, but it's a sort of mess in the middle. And this is Abell 2052. So the absorbing gas, you can see it. And so they're common. A big problem is, will too much gas accumulate? If you use in a gigayear in Centaurus, you'd accumulate 10 to the 10 solar masses. In Perseus, 10 to the 11 solar masses. So that's a lot of cold gas to accumulate. But what is too much? There is a lot of cold molecular gas observed in these objects. Centaurus has got 10 to the 8 solar masses of observable CO, well, molecular hydrogen, and some of them have 10 to the 11. Maybe there are lots of ultra cold clouds. It's not well known, but the cooling time of clouds, molecular clouds of about 10 to the 10, sorry, 10K is around a week, a few weeks. And you have to keep them warm in order to see them. And imagine there's nothing that keeps them warm. Then my preferred solution is that it is low mass star formation. The high pressure at the centers of these cool cores, and the product of N and T is 10 to the 7 per cubic centimeters Kelvin. In our interstellar medium, it's around 3,000. So this is much, much higher than the interstellar medium of a galaxy. This can lower the gene's mass. And this was pointed out by Mike Jura in 1977. And I've worked on it in 82 and with Gary Furlan in 94. So this means low mass star formation is probably brown dwarfs. It's forming masses of brown dwarfs. And it's interesting that starting about 15 years ago, Peter Van Dokkum and others, in M87, it's been inferred that there's a bottom-heavy IMF observed in nearby ellipticals. And the bottom-heavy IMF means there's a lot of low-mass stars or brown dwarfs or something. And for the young people here, I would just say one of the things in astronomy which is not explained, there are various things that you must not do in astronomy, and that is you should not change the IMF. The IMF has been provided for us, it's well measured, and it's the same if you go to our galactic neighborhood, if you go to the center of an elliptical galaxy, if you go to anywhere in the universe, redshift 10 galaxy, it's assumed it's always the same. And I'm saying maybe it ain't, particularly at the centers of these objects where you can have them bottom heavy. They're observed to be bottom heavy, but there is a reason they're bottom heavy. It's because cooling flows have dumped a lot of stuff there. Anyway, we'll see how this plays out over the next 50 years. This is just to show you gas in, this is 1275 in the Perseus cluster. This is what it looks like, and this is from a HST image in narrowband image taken in the 20 years ago or so. Going from there up to there is about 50 kiloparsecs. So let's give you the scale. This is enormous. This is the thing that I called a squash spider in the earlier image, only in more detail. And a lot of this, you can't really, you'd have to turn all the lights off to start seeing the detail. There's a lot of detail in these filaments, and some of them are kiloparsecs straight. I'm sure they're magnetized in some way, and some of them are there is some star formation in some, in particular this area here, but generally there's no star formation at all. This is CO observations. And then with CO, we're looking at Abell 2597, Grant Tremblay and others, and this is new work from Tom Rose, is showing this is CO observations, CO, HCN, HCO plus, and so forth, where these are looking at the spectra of the nucleus of the object, and you see that redshifted, that there's absorption lines. So there's molecular clouds at the center of this object, Abell 2597, which is a cool core cluster. Come on. There we are. And I compared my rates with those made by X-ray imaging, comparing what's happening on large scale to small scale. And the ratio where compared to the large scale rates, it appears there's a region in space where feedback is operating. I'm not saying there is not AGN feedback, there is, but AGN feedback is not 100% efficient. And in some objects, it's not efficient at all, and other objects, it's highly efficient. So feedback itself is an inefficient process. Take away from that. There are out there objects with cooling flows running wild. This is this is redshift 0.35, 0.36, 0.6, and you can see all these filaments and everything all over the place. Michael McDonald and others have made a lot of work on this object, the Phoenix cluster. It's got a quasar in, and they get M dots of 3,000 solar masses per year or more. So this thing is really, it's on steroids. Just before I move on to the next topic, is hidden cooling flows. They're common in even massive elliptical galaxies. All you students have been told that elliptical galaxies are red and dead. They're certainly red, but they're not dead. They've got cooling flows at the center of them, typically a solar mass per year, but that's not that much different from our own galaxy, excepting that solar mass per year can't be going into normal stars. All of this is testable with JWST MIRI spectroscopy. If we can see the neon 6 line at 7.6 microns, we got 10, there were 10 proposals tried to do this the last round, and we didn't get one through, not surprised. But this line comes from gas at about 3 times 10 to the 5 K. And if we could see it, it would sort of indicate that gas is continuing below the X-ray emission temperature. And the strange thing is this Phoenix cluster is full of neon 6 emission, buckets of it. In fact, it has too much. Now I'm going to go to the AGN. This is a typical picture of an AGN as made by an artist, but you get the idea. Material swirling around a black hole that may or may not have a jet, but it has a strong corona somewhere here. The strong corona is giving hard X-rays. This depends upon the mass and so forth, the scale of it, can be black body emission. And there is this idea of reflection spectra, which there's a direct power law to the observer, and the corona is also radiating the disk. And if you can look at the reflection spectrum, that reflection spectrum is going to have emission lines in, and you can then see how that line is being distorted by the GR, by the basically Newtonian Doppler shift, the special relativistic transverse Doppler shift and beaming, by GR, gravitational redshift, and you get this skewed line, which looks like this. And I, together with, the computations were done by Luigi Stella, who many of you know, in 1989, for a Schwarzschild black hole, you get this broad line, and the most likely line is fluorescent ion line. So we started talking about broad ion lines, and this is what a Kerr black hole you get from the calculations by Ari Leor a couple of years later. So Randy Ross and I started making computations of reflection spectra where they look like that. And then when you broaden them, you end up getting them looking like this. So this is relativistic broadening of this raw spectrum. And you get a what's called Compton hump, the broad ion line, and a soft excess. And that's what X-ray spectra should look like. And many of them indeed do look like that. And this was the first one, which came from the first CCD, X-ray CCD on a satellite, the ASCA satellite, a Japanese satellite, and led by Yasuo Tanaka, who was the PI of the satellite. We ended up getting over 200 kiloseconds of time, at a, which was amazing. And this is the result that we got out of it. So what does and this is the first broad line. It was published in 95. At the end of 1995, I wrote another paper, a paper saying why all the papers that had come out after we published this were wrong, because many people immediately sort of sat down and wrote a paper saying this can't possibly be a relativistic line, it's because of X, Y, and Z. They were all wrong, but anyway, so I had rather hoped that people would cheer, when this came out, because what we've got is spectroscopic observations of the innermost regions of an accretion disk very close to a black hole. We're probing very close to the black hole. And yet all people would say was, I don't think we are, it must be something else. And it was a very strange time. And there's Yasuo Tanaka, and me and my wife and Rich Mashotsky and Claude Canizares, and I can't identify him, but never mind. We were in, before ASCA was launched, we spent, no, after ASCA had been launched, we spent 3.5 months in Japan. And it was not a very hot summer. You can see it was a wet summer. I'm told that better than the hot summer. Let's go. And now we've got CRISM. What does that show? It looks like this. And so this is the advance from 95 to 2024 or 2025. And you can see it looks very similar. There is a very strong narrow line, the fluorescent line, which comes from outer material, but otherwise it's all looking pretty similar. And this is from CRISM Resolve. This is what the spectrum looks like. And this paper is not yet out, okay? So I'm showing you, some of you will have seen it, but it's new. This is this narrow line, and then there are two absorption lines, principally. And so basically the broad iron line, this is the model of the broad line. It's being affected by the absorption, but it's not very much. And so it's giving us the value that how broad the line is telling you how close you're going to the black hole. And this is giving us the result that it's a highly spinning black hole. This is a kind of reflection, just that there are lots of reflection spectra around. This is a beautiful one from Don Walton, from a galactic transient that flared up. If you look at this line, this is what happens as you increase the spin. As you increase the spin, the ISCO, the innermost stable circular orbit around a black hole, depends upon the spin of the black hole. And as you spin the black hole up, so the innermost stable orbit moves inwards. And so maximum spin. Maximum spin means you get more reflection from the innermost regions where there's the highest gravitational redshift. So this is a highly spinning result, and this is the low spinning result. So if you can measure where that part of the spectrum between 2 to 4 keV, you can actually measure the spin. And what we get for, MCG6 is around 0.98. Sometimes emission comes from within 2 RG. This was from a student of mine, Michael Parker, on Marconium 335, where you can see here where this is in blue, it's the unblurred emission, and this is the iron line, and the data are in the black points, and you can see this how the iron is emission has been pulled over here, and there is still an emission from distant material. That's why there's a peak there, but otherwise, including the Compton hump, it's being dragged over. And a reflection-dominated spectrum like this is rare, but enables us to conclude that emission is within 2 RG. This is, my pointer is refusing to change. There we go. And just in case you wonder what happens about neutron star systems, Renee Lidlam has sent me this example of an CRISM spectrum of a neutron star X-ray binary, Serpens X1, where you can see 2 lines. One is from hydrogen-like iron and one from helium-like iron. I think this is beautiful. And from it, she concludes that the innermost radius is 1.01 to 1.23 times the radius of the ISCO, and that is in RG. So this is just a spinning neutron star with an accretion disk around it. Sometimes enormous outflows are seen, and this is PDS 456, and this is, people call them UFOs, an ultra-fast outflow, and you see all these absorption lines going up to nearly 10 keV from this. It's the outflow in PDS 456 was known from XMM and other work earlier, but this is CRISM result is just beautiful. I'm now going to finish by talking about the last region. I want to get closer to the black hole. How close can we get? Well, let's look at the plunge region. So here we've got this, I think it's Niagara Falls. And so you've got to the region, if you can imagine being on a little boat as you approach the plunge region, where here you can paddle and get away from it, but you get there and you have to go into the black hole. So the plunge region is the ISCO. What's going on there? This is a NICER, which is on the International Space Station, light curve of MAXI 1820, which was a black hole star, a normal star binary that flared up in 2018. And I was lucky enough to get much of the new star data from this object, and a student and I worked on it hard. And this is what the light curve looks like. It was in the hard state and then the soft state. And in the hard state, you could see it had this characteristic Compton hump and reflection spectrum, broad line fluorescent ion line. But the soft state looked like this. And basically, there was some residuals that looked rather like this. But when you look, they're at the wrong energy. It's all happening around 8 keV, peaking at 8 keV. And what I realized was that if I went and played around with the data, that this excess here could be explained by adding another black body. So adding an extra black body pushed everything a bit to the right and mopped up this bump. So this means there's an extra black body in this emission. Where would you put the extra black body? Well, why not at the ISCO? And if you do that, the ISCO is at about 50 to 60 kilometers out in this system. And you only need it to be 1 to 2 kilometers wide. So it looks like it could be something around there. And then a possible hand-waving explanation is that magnetic fields in the outer region are hanging on to some of the material as it goes over the edge, as it were, ready to plunge in. And you can get emission just from the, very close to the ISCO. We published that in 2020 to a resounding silence from the community as to, wow, isn't this really exciting to nobody taking any notice. Anyway, there's one person took notice. That's Andrew Mummery at Oxford. He is a theorist. He was a student of Steve Balbus and worked a lot on what's going on in the innermost regions of disks and so forth, and GR. I'm not a relativist, so I'm not going to delve into any of that, but he went and built models for what might happen from emission at the disk, at the ISCO, and that model was called Full Kerr, and he fitted it to the data. And together we published a paper last year about this. And his result for where the spin of a black hole is very similar to what my student Douglas Buisson got in 2019. So an extra black body can plausibly be due to mild stress at the ISCO. And this gives us observational access to the innermost accretion in these objects. And this is probably the closest observation to the horizon of a low spinning black hole. So I'm now taking you through a wide variety of observations in X-ray astronomy. They've kept me very busy and interested, and I can see it lots of ways it can continue. I just hope that what's going on across the Atlantic is not going to screw it all up, but let's not talk about that. This is the Perseus cluster. Right at the end, I managed to get a legacy program accepted, which would give us another 3 megaseconds on the Perseus cluster, so tripling and quadrupling the total amount of data, and we can do a much better job of exactly what's going on using Chandra. And I've got my fingers crossed that Chandra will survive long enough to make these observations. And I'll end it there. Thank you.
Okay, thank you very much, Andy, for this recollection of results. And so I open the discussion. I encourage graduate and undergraduate students to not to be shy and make questions, and it's open to everybody, of course. So just raise your hand and someone with the microphone. Okay, so undergraduate.
Sorry, you probably said it, but I missed it. In some of your early slides, you said that the thermal energy should be constant on a long time, on a short time. I probably missed it.
I was talking about maintaining the thermal energy content constant within a cluster. I mean, it's possible it is going up and down, but if we want to make it constant, then we needed the velocity that I said. And there's no strong evidence. I mean, we would only have to wait a cooling time if, in fact, there was no energy being supplied before there was catastrophic cooling taking place in these clusters. So I think that something has to be pumping energy back in. Okay.
Gianfranco.
I'm an undergraduate student.
We all are.
Unfortunately, no. But yeah, so you mentioned in the first part of your talk about these measurements from calorimeters, actually.
Yeah.
And of course, that there is less turbulence than expected, at least a factor 2 probably.
Yeah.
From the, so and there is probably a beautiful plasma physics behind that in order to explain this. But
Yes.
in any case, there is, however, a possible clash between these observations and other observations. For example, radio astronomers tell us that when they do Faraday rotation in galaxy cluster, they do observe magnetic fields that are tangled on scales of a few kiloparsec, maybe 10 kiloparsecs. So this implies that motions in the intracluster medium must be super alphenic, should win the Reynolds stress in order to tangle these magnetic field lines. That is 200 or so kilometers per second on scales of 10 kiloparsec and not maybe 50, 100 that's measured. So there is a potential clash that, I mean, can be explained or not, thinking about volume filling of the motions, time scales of the motions and so on. Can you comment on that, if these measurements are really the end of the story or what's going on?
I think they're only the start of the story, and we need your help with modeling, and also we need to get many more observations. But we are stifled in a way by the PSF of CRISM is about half energy width is 1.3 or 1.4 arc minutes when we're trying to look at clusters where 10 kiloparsecs is much smaller than that. So I think we actually would have to wait for Athena to get them on this sort of scale. So Athena is a possible X-ray mission, but it's ESA's X-ray mission that hopefully will launch in the 2030s, late 2030s, and that will have even a 10 arc second is going to be pretty good for doing this kind of work.
Yeah. Don't miss the opportunity. No, Graziella, you already did it. Another one. Massimo.
So you mentioned search for neon 6 as a tracer of your hidden cooling flow. What about in the soft X-rays from CRISM? If the gate valve will open, will you have a smoking gun for your hidden cooling flow?
I'm going to be, I think it will be very interesting once the gate valve opens and we do have the soft X-rays. I would say, however, that actually the gratings actually have better resolution below 1 kV than CRISM does. As you know, it turns out the resolution of a CCD, or you know, is measured in EV, and the resolution in a dispersive spectrometer is proportional to the wavelength, you know, fixed wavelength. And so I think there's the possibility, particularly if it gets down to 0.1 kV, which it should do, of detecting some emission back down there, which would be exciting. So.
Yep.
Hello, Babs. I'm actually an undergraduate student.
Oh, great.
And because we are doing a project on galaxy clusters, I have this question. You briefly mentioned turbulence effect on galaxy clusters.
The which effect?
Turbulence.
Oh, turbulence, sorry.
Turbulence, yes.
Yes.
And since we're doing this project on it, I want to ask, is thermal effect of turbulence should be considered in the studies? Is it viable? Is it the latest evidence are indicating that thermal turbulence is actually doing something in the cluster or no? And if you want, in the end, you can just give us a direction for undergraduate students for their future studies on the galaxy clusters, which might be a promising subject topic for the future studies. Thank you.
Sure. Thank you for the question. Turbulence is a very complicated subject. Gianfranco and I spent yesterday morning discussing it, and I would say it is a very complex subject. And the Kolmogorov turbulence, where you get energy going through each scale, is just a special case. And what the COMA results are suggesting is there isn't this setup where it just naturally goes down in scale, hopefully to dissipation. But quite honestly, where we go from here in a way of helping undergraduates to dive into it is not simple. I mean, I would say it is a very complex subject, and you can read Gianfranco's 75-page review on it, but there is wait and see, I would say. Perhaps look at some of these papers, but I would say there's still a lot of people in X-ray astronomy who think it surely must be turbulence. But I myself am not sure. And the data are suggesting it's not the sort of simple kind of turbulence that's been predicted by many of the simple numerical simulations. So it's a tough subject. And it's, you know, we are just at the crux where something is changing, and it's exciting, and it's observationally driven. This is how astronomy advances. It's a highly observationally driven subject. You're very lucky to make a theoretical prediction in astronomy that works out, and nobody will believe you until it's observationally tested and so forth. But this is an observationally driven area. Maybe we're all confused in some way. Maybe there's somebody will put their hand up and say, oh, I know what's going on. And it's nothing that I said or Gianfranco said or anybody else has said. And it all is transformed. Maybe it's got something to do with dark matter. I don't know. But we have yet to find out. Okay, it's a messy subject.
Hello. Andy, it's Remo Ruffini colleague speaking. Can you hear me?
Sorry.
Who is? He's there.
Oh, I'm sorry. Yeah.
Yes. Fascinating talk, very vast. But later, of course, we are very interested in dark matter. And you briefly mentioned And this could have a very important consequence. But quite apart from this, which we are working in Europe, there is been a renewed interest of this last stable orbit, the so-called LISCO I introduced with Wheeler many years ago. And recently we have published in Physirev Letter an article calling attention on the irreducible mass. We are working on that, and I would like you to look at it because we have the possibility eventually to measure in black holes not only the mass but also the irreducible mass, and maybe to have observational consequence. In particular, in gamma ray burst, we have been able to measure for the first time black holes in GRB, which are of the order of 2.3 solar masses. So we are going to publish this in a few days. And there again, the role of the irreducible mass is essential. I will send you some material and force myself to publish them very shortly. And my collaborators.
Thank you, Remo. Please do send me this stuff. Yeah.
And I'm very happy to be still in touch with you after so many years.
Yes, I can remember you from a long ago.
Okay.
Yeah.
Yeah, Carlo.
Hi, thank you for the very nice presentation. I have a question about the coma cluster. You were mentioning that is a system which is probably merging with some interaction, and then you were showing these bulk velocity measurements with the difference kind of 300 or 400 kilometers per second. So the question is, are we measuring the relative velocity of the subsystems or anything else?
I think where the observations are, the subcluster, I think, has gone through and is down to the bottom right, the southwest. I believe so. There's been discussion about exactly what the geometry is. And so I think quite a lot more observations need to happen. But it is, I mean, the simple result is there are fairly large differences in velocity between the north and the south, but within them, there's very little difference in velocity and dispersion. So that's the answer. And it's not what was expected, and people would have expected a much, I mean, maybe the next observation will turn it all around. I don't know. I know of one more observation which is unpublished, which also has a low dispersion. But I think probably within a year or so, there will be 5 or more observations, more, I hope so anyway. And there's also going to be many observations of other clusters similar. So it's early days.
So, come on. You have the chance. Yes, Miriam.
Hi, thank you. So maybe a provocative question. So if the cooling flow is hidden,
yes.
So it means that it is there. So it is actually cooling. So why do we still need the AGN feedback? You briefly mentioned that. You said the AGN feedback is still there, but could you comment a little bit more on that?
Yeah, I think the big problem with AGN feedback in clusters is there's some sort of large hysteresis. When the gas cools, how does it, at a distance, how does it communicate with the jetting that's forming at the black hole? Is it communicated by sound or material? If it's due to the flow of material, that takes ages. And one of the problems I have with it is fine-tuning effects, that if in fact there was a way of coupling the feedback, which was argued for long ago, that basically stuff cools rapidly in one place and falls in, and so lights up the engine, so the engine produces more energy. The problem with that is you'll end up with 10 million years between the two, and the whole thing will be a big mess. So what I was saying in terms of efficiency, I was talking about comparing what's happening at 30 kiloparsecs, say, with 3 kiloparsecs. The hidden cooling flow is within 3 kiloparsecs. And I'm measuring m dot of, say, 10, and somebody's measuring 100 at 30 kiloparsecs. That means that basically the feedback must be working in order to stifle it down that much. So that's what I meant. That was what I was trying to communicate. But it's probably, these things are continually going up and down. But up until now, it's generally been assumed, and I've been in talks where people have said, oh, I've said, what happens to the cooling? And they say, oh, I switched off cooling because it's exactly balanced by my heating. Okay, and that's nonsense.
So, a couple of more final questions before I ask something. Is working this one?
Don't think
shit, it does. So last chance to. Okay, so I'd like to ask Andy some wise advice and suggestion, especially for the young undergraduate and graduate student, why they should consider X-ray astronomy as a possibility for their career.
X-ray astronomy is full of exciting objects to look at, exciting ideas. We're dealing with the smallest things in the universe, the black holes, and I think we're doing a fantastic job. We can observe very close to the black hole. We can try and see how they operate. There's a long way to go. We also can look at the largest objects, the clusters of largest bound objects are clusters of galaxies. We can find out what's happening with all that. And dark matter is a key thing there. I have no idea what it is, but you'll get a Nobel Prize if you can work that one out. And there's also, the way in which the universe works. And there's lots of excitement happening involving JWST, is finding out all sorts of odd little red dots are, on many people's minds. They're not detected in X-rays. Why not? I think it's because there's a lot of gas around them, but it may be something else. Why, are accreting black holes, is what we're seeing really outflows? I showed you PDS 456. I'll share with you. I don't think it's what people say it is. Everybody says it's an outflow because that's the simplest solution. I think it's absorption from material within a few RG. Okay? If you think about what's happening with one of these objects, okay? Now, look at the sun. Let's forget about PDS 456. Let's talk about an accreting AGN with a mass of 10 to the 10 million solar masses. Its corona is not much bigger than the sun's corona, say 15R sun, okay? So we're talking about a very small object, speaking, and yet it's producing a luminosity that is 1 trillion times larger than the solar corona, trillions. It's also rotating on a time scale, which the sun rotates in a month, okay? This is rotating, on time scales of hours and days. So, I think the sun, I have a little solar telescope at home where I look at prominences and things. And you know, that all this activity comes out of the sun because it's differentially rotating. Here we're dealing with something differentially rotating, where the rotation speeds, orbital speeds are up to, you know, up to velocity of light, and you've got magnetic fields involved. It's going to be an incredible light show and mess, and there will be absorption on the sun. On my little solar telescope, I can see things called filaments. They're dark filaments. They're produced by Balmer absorption. Balmer absorption is seen in little red dots. Okay, I'm not making a big connection there, but there's going to be all sorts of absorbing material. X-ray absorption is going to take place, as well as X-ray emission. And I've done simple calculations, and you can find a paper from me in 2020 where we explain the UFO in a narrow-line seafoot one called IRAS-13224. We explained it in terms of absorption rather than an outflow. Okay, so I think it's possible. I'm just, you know, if you like, I'm just letting my mind wander. And I'm having fun. I let my mind wander around a black hole and try and think what might be seen and what might be going on. And where there's emission, there's going to be absorption. What will that absorption look like, and so forth. So we'll have to see how that works out. I haven't written anything yet, but I'm just saying there's lots and lots of things to do, which are, I think, important. You can have an exciting career in something which is at the forefront. I just hope that the support for astronomy continues in several countries. I'll leave it there.
Okay, thank you very much. As you know, Andy is visiting the observatory till tomorrow evening. He's sitting at the 4th floor of the Battiferro building in the Stefano office. And so you may come to visit him to ask questions. And I remind you that this afternoon at 2:30 p.m., there is a meeting with PhD and undergraduate students that want to meet and chat a bit with Andy. There will be coffee and cookies. And so, I mean, you are welcome. And okay, so let's thank Andy for this beautiful lecture. And you for coming. Okay. Thank you.
Good.